Okay, good afternoon, everyone. So we're very happy today for the GTP seminar to have Fiona Torzewska from University of Bristol, who's going to tell us about topological quantum field theories and homotopy cobordisms. Fiona, please.
Thank you. Thank you for the invitation. So most of the things I'm going to talk about in this talk are contained in this paper of the same title that's available on arXiv at this number if you want to go and have a look at it. Okay, so let's start off with some motivation. So why did I start working on this? I was interested in understanding particle statistics in topological phases of matter. So the kind of pictures you should have in mind are things a bit like this. So what are these pictures very roughly supposed to show? If we look at this left-hand bottom box, the bottom of this box represents some physical system with some point-like particles in this system. And then going up the box, we have time, and we see how these particles move in time. And lots of things might happen. These particles might fuse together, they might braid around each other, new particles might be created. And then at the top of the box at fixed time, we again have 4 point particles. And then on the right, we have a slightly more complicated situation where we have these loop-like particles as well. So what this sort of yellow picture on the left is supposed to show is we have like nested, so we're still in 2 dimensions, we have 2 loops nested one inside the other, and then we end up with this kind of particle trajectory that looks a bit like a pants cobordism with one leg moved inside out. So this is the kind of thing we might get in 2 dimensions, and then on the right we have some loop tracing out the surface and some point particle knotting inside this surface. And we might also have things in higher dimensions where we can have knots and links and surfaces in 3 dimensions which trace paths in 4 dimensions. But my drawing is not very good in 4 dimensions, so I just have these pictures. Okay, so how mathematically can we model these kind of particle trajectories in topological phases? Well, there's several different categorical formulations which aim to do this. So examples include motion groupoids, mapping class groupoids, tangle categories and their generalizations, defect cobordism categories, embedded cobordism categories. Many of you, I'm sure, will have come across these types of constructions. So what I'm interested in here is understanding representations of these kinds of categories, which are invariant up to a notion of homotopy equivalence of the complement of the particle trajectory. So we're restricting ourselves to a very specific type of representation here, and representations that use this kind of information about manifolds and embedded submanifolds are quite common in the literature. So on the kind of topological quantum field theory side, we have things like Yetter invariance, Kitaev, Digraph-Witten, and Quinn. But then also on the more topological side, we have similar constructions purely for obtaining representations of knots and representations of braids. For example, the knot group, which looks at the complement of a knot, or the Artin representation of braids. In general, when we consider these categories which model particle trajectories, and then we take the complement of these trajectories, these generally won't be compact manifolds, and we won't necessarily fit nicely into existing theories of manifold cobordisms. So we want to think about how we can deal with this slightly more general setting. So thinking of representations as functors from these categories modeling particle trajectories into vect, these functors might factor through other categories on the way that might be easier to work with than the category we started with. So what we do here is construct a category of cofibrant cospans of topological spaces. And of course, I'll say what I mean by this. And functors from each of the categories we named above can be obtained with target this category of cofibrant cospans roughly by taking the complement of these particle trajectories. So the first thing I'll talk about is the construction of this category. And then I'll also talk for a bit about what motion groupoids are and how explicitly, in this case, to obtain a functor into this category of cofibrant cospans. And then I'll also show how Yettas, TQFTs associated to finite groups can generalize to give us functors from our category of cofibrant cospans, which really are explicitly calculable, and we can get particle statistics out of these functors. So the first thing I'm going to do, talk about the construction of this category, COFCOS of cofibrant cospans, and then I'm going to take a subcategory with a certain finiteness condition, which I call HOMCOB for homotopy cobordisms. I'm then going to talk about a functor from the motion groupoid of a manifold into HOMCOB. And then lastly, I'm going to talk about this family of functors from HOMCOB into VECT, which take as input a finite group, G. Okay, so we start with the categories of cofibrant cospans and of homotopy cobordisms. So if we take a triple of spaces, X, Y, and M, a cofibrant cospan from X to Y is just a diagram of this form. So a map I from X into M and a map J from Y into M, such that this map, which I call I, J, and these angle brackets. So what do I mean by this map IJ? So X disjoint union Y is the co-product of X and Y in the category of topological spaces. And so if we have a map from X into M and a map from Y into M, then using the universal product, we have a unique map from X disjoint union Y into M. So these angle brackets is just my notation for this unique map from X disjoint union Y into M. And we put the condition on this unique map that it must be a closed cofibration. Now I'm going to talk more on the next slide about what I mean by closed cofibration. But I'm just going to say first that then we just introduced this notation that for any X and Y in top, the category of topological spaces, so for any X and Y topological spaces, we just write COFCOS XY for the set of all cofibrant cospans from X to Y. Okay, so what do I mean by closed cofibration? So here I mean Hurwitz cofibration. So cofibration in the category of topological spaces. So I'm going to talk about the precise definition, but then I'm going to say some things that hopefully will give some intuition, even if it's obviously very hard to absorb a definition you're unfamiliar with in the talk. But if we take, so just looking at this diagram, if we take spaces A and X and a map I from A to X, then this map I is said to have the homotopy extension property if for every map F from X into some other space Y, and every map H from A cross I, such that the outside of this diagram commutes, so I followed by F commutes with the inclusion of A into A cross 0, composed with H, then there exists a unique map from X cross I. So what we're saying is that if we have a homotopy of A cross I, and then just a map from X itself, this extends to a homotopy of the whole of X. And we say that a map I from A to X is a cofibration if it has the homotopy extension property for all spaces Y. And then by closed, I just mean that the image is closed. So there's a few ways you can think about this. So cofibrations are in particular homeomorphisms onto their image. So you can just think about this as an inclusion with some extra properties such that it behaves nicely. But for the purposes of this talk, you should think of this, if you're familiar with cobordism categories, and how in cobordism categories we can compose cobordisms by gluing. And this works nicely with the identity, precisely because boundaries always have a collar neighborhood, which look like the boundary cross I. You should think of this condition as a generalization of that. So this is what's going to allow things, our cospans, to compose nicely such that we have an identity in our category. Okay, so what does an example look like? So we could have a cofibrant cospan where our X and Y are both copies of S1, and one copy, and then our M is a copy of the disk, and one copy of S1 includes into the boundary of the disk, and another copy of S1 includes somewhere into of the disk. We also could take a picture like this. So this picture is supposed to be the unit box. And then embedded in the unit box, we have a copy of S1 in the top and two copies of S1 in the bottom, and then this embedded manifold. And I can obtain a cofibrant cospan just by taking the complement of this embedded manifold. So my X is the unit square set minus two copies of S1. My Y is the unit square copy set minus a copy of S1. And then M, the unit box, set minus this embedded manifold. Now, note that if we take the cospan, which is just three copies of the same space, and the identity maps, this is not a cofibrant cospan. So the way to see this is that we have this condition that we must have X disjoint union X into X is a cofibration. And a cofibration in particular must be a homeomorphism onto its image. So this map, which sends like two copies of X onto themselves, will not be a homeomorphism. And so if you're familiar with like Benabou's construction of taking as input any category and obtaining the category of spans or the category of cospans, this would usually be the identity. So this is not quite the same as what we're doing here, and that's why we still have some work to do to prove that we really can obtain a category in this way. That is a cofibrant cospan. So if we take two copies of X and then as our middle space, X cross the unit interval, and we include X at X cross 0 and X at X cross 1, then this really does give a cofibrant cospan. And how do we prove that this really is a cofibrant cospan? So we want to check that if we have any homotopy from X disjoint union X cross I into K, and then just a map from X cross I into K, we really can extend this to a homotopy on the whole of X cross I. And the way to do that is just observe that from I cross I, there's a retraction which takes any point in X in I cross I, and sends it to this point X prime, that is the unique point with the unique endpoint of the line which goes through X and this point Z outside of I cross I. And so this gives a retraction which sends I cross I to just the bottom of this box and the two sides. And then this is precisely where our H and our F are already defined. So just composing with this retraction gives us a way to extend to a homotopy. And so we get that this really is a cofibrant cospan. Also, if we take any concrete cobordism, so here I mean a cobordism before we've applied any equivalence relation, this uniquely gives us a cofibrant cospan. So what does it mean to be a cobordism? We have three smooth-oriented manifolds, X, Y, and M. And if M is a cobordism from X to Y, this means there exists a diffeomorphism from X with the opposite orientation, disjoint union Y, into the boundary of M. So we can construct our maps I and J just by using this map phi and just forgetting about the smooth structure. And another example, if we take any CW complex together with a pair of disjoint subcomplexes and the inclusions, this will also give us a cofibrant cospan. Okay, so we can also construct a composition of these cofibrant cospans. So if we take as input two cofibrant cospans, one from X to Y and one from Y to Z, then we construct the composition of these two cofibrant cospans by looking at the following diagram. So what is this diagram? This diagram is constructed by taking the push out over this span YJ into M and YK into N, sorry, in the category of topological spaces. So this M disjoint union over YN, what that means is take the disjoint union of M and N and then quotient by the images JY for each point in Y, quotient by saying JY is equal to KY. So this is like a gluing map, really. And so hence we have a magmoid. So what do I mean by a magmoid? Just that we have objects, morphisms, and a composition, but we don't yet have any axioms. This isn't an associative composition. We don't yet have identities. Okay. So we're now going to apply an equivalence relation on our cospans, such that we do obtain a category when we take the quotient by this equivalence relation. So if we have two cospans from X to Y, we say that these are equivalent if there exists a commuting diagram of this form where I can draw the cospans, the two cospans, with a map psi from M to M prime, such that psi is a homotopy equivalence. And this gives us a congruence on our magmoid COFCOS. So let me just draw a picture to give an idea of what this equivalence relation looks like. So remember, before we had this example of a cofibrant cospan, which was the disk. And so letting Y be this copy of S1 that we glue, that we included into the interior. Then if we try and compose this with the identity, that's the cylinder S1 cross I, then that looks like sticking this red cylinder on top of this disk. But this is homotopy equivalent to shrinking the cylinder all the way back down to the disk. So that's the kind of thing that this homotopy equivalence relation allows us to do. And it's not straightforward to see that this really does give us an equivalence relation. This uses quite a big result due to Brown. And here we really need that we insisted we had this co-vibration property. So what this result of Brown says is that precisely when we insist that this map, map from X disjoint union Y into M is a co-vibration, then what happens is that if we consider this condition where we have some psi, which is a homotopy equivalence, that is actually exactly the same as considering psi such that it has a homotopy inverse which also commutes with the diagram and all of the maps that we need to go through to get our homotopies from psi prime phi and phi psi prime to the identity also commute with the cospans. And we need that property to prove that we get an equivalence relation here. Okay, so then once we've proved that we have an equivalence relation, it's then fairly straightforward to check all the things we need to see that this really does give a category. So we can confirm that the identity really does behave like an identity, and the composition, if we just do the same composition on representatives, this really gives an associative composition of classes. Okay, so we have our first category. To construct the kind of representations into vect that we're going to want, we would like these representations to have send objects to finite dimensional vector spaces. And if our spaces are too wild, then it's going to be hard to construct functors using the fundamental groupoid, using homotopy properties of the spaces, which ever give finite dimensional vector spaces. So we're now going to take a subcategory of our category of cofibrant cospans, such that we have some finiteness conditions. Okay, I've got ahead of myself. First, I'm going to talk about the monoidal structure on this category, COF-COS. So there's a functor which goes from top H, so top, by top here I mean the category of topological spaces, so spaces and continuous maps. Then by decorating it with this H, I just mean I'm restricting to homeomorphisms. So if we take this category with only homeomorphisms, then we can construct a functor into the category COF-COS. And this we just do by taking any homeomorphism F from X to Y and sending this to the cospan, which goes from X to Y. And we take M to be Y cross I. And so then on the right-hand side, we just include Y. So a point Y gets sent to Y comma 1. And on the left-hand side, we do the composition of applying F and then including into the bottom. So a point X gets sent to F of X 0. And this is exactly the same mapping you use to obtain mapping class representations from topological quantum field theories normally. And so then there is a symmetric monoidal category with underlying category COF-COS. The monoidal product is just given by on objects taking disjoint union. And then this extends to cospans by just taking disjoint union of all spaces, and then the disjoint union of the maps. And then to obtain all the necessary maps, the associators, the unitors, and the braidings, you can just apply this functor to the corresponding maps in top. Okay, and then now we're going to add a finiteness condition. So we say space X is homotopically one finitely generated if this pi XA is the full subgroupoid of the fundamental groupoid with base points A, a finite set. So what we're essentially saying is that the fundamental groupoid is always finitely generated if we choose some subcategory with a finite number of objects. So these spaces aren't allowed to get too wild here.
Sorry, can I just ask a question here?
Yes.
Is there a reason to use the fundamental groupoid here? Wouldn't this followed by just stating that the final group for every connected component is finally generated?
Yes,
Well,
that
is that what you
would
mean,
be,
maybe, or?
Yes, no, it would be exactly the same thing. It's just that later on, it's going to be useful to formulate things in terms of the fundamental groupoid. And so it's nice to kind of use the same notation throughout. But yeah, that would be exactly the same condition.
I see, thanks.
And then taking this finiteness condition, we get a symmetric monoidal subcategory, Homotopy, where our spaces are, so I use this chi to denote these homotopically one finitely generated spaces. Chi, our morphisms are cospans which only include homotopically one finitely generated spaces up to the same equivalence relation, composition by push out, and then our identity, taking this cylinder over the space. And so then before I move on to talking about motion groupoids, are there any other questions about the construction of this category?
Yeah, I had one more question. Where you saw, I suppose, there is a good reason that you use Fourier-Ridge cofibrations as opposed to the Serre cofibrations. Where would the construction break if you insisted on just using Serre cofibrations?
Yes. So at this stage, not yet.
Oh, okay.
When I construct the functors, that will be where the fact that these are closed cofibrations becomes really important.
Oh, I see. Okay.
And so, yeah, the way to see this, so I mean, I guess you're familiar somewhat with model categories. So if you use Serre cofibrations, you're essentially working in the Serre model structure on topological spaces. So your equivalences should be weak homotopy equivalences. But if you want to work with your equivalence relation being homotopy equivalences, then to match up nicely, your cofibrations should be in the Strom model structure on topological spaces where your cofibrations are closed cofibrations.
Right, yeah, that's why I was wondering. And so I guess you're saying you actually do need the Ström model structure here for later constructions to go through.
Yes, yeah,
right.
And otherwise you're probably, I expect you can do this with any model structure, and then but then your equivalence relation has to adjust to the model structure you're working in.
Okay, all right.
Okay, so motion groupoids. So this was a big part of our motivation for doing this construction. So I just want to talk a bit more precisely about what we mean by a motion groupoid. So if we take a manifold and submanifold pair, which we denote M underlines, this is a pair of M and A. So the type of thing to have in mind here should be taking M to be some manifold and A to be the boundary. So this is some like globally fixed subset of the space. Then we define what we call a flow in M to be a continuous map from I, where this boldface I just used to denote the unit interval, just to make it a bit shorter. So this F is just a path, which has image in this top MM. So this is continuous maps from M to M, where this H means everything's homeomorphisms. So homeomorphisms M to M, where I've topologized this with the compact open topology. So if you're not familiar with the compact open topology, it doesn't matter at all. But the point is, it's a continuous path of homeomorphisms from M to itself. And then this A just means they fix A. So for example, they fix the boundary. And we insist that they start at the identity. So a flow in M is just a continuous path of homeomorphisms of M starting at the identity. So for example, if we take F at all T to be the identity, this is going to be a flow. We could also consider M to be the unit circle and take A to be empty, and then we could have some flow which gradually rotates the circle so that by the time we reach the end of the path, we've rotated the circle by pi. And so then what does it mean to be a motion? So we obtain a motion by taking a flow and then considering a subset of our manifold, dropping in some subset. So a motion in M is a triple consisting of a flow F, a subset N of our manifold, and then N prime is just the image at the end point of the flow of N. So I'll give a picture, which hopefully, okay, I'll give this picture first, and then I'll give another picture that hopefully will make things a bit clearer. So this light gray space is this space of homeomorphisms from M to itself. These flows are these paths in this space. So for example, this red path that starts at the identity, and then this is being considered as a motion from N to N prime, which means that its endpoint must be a homeomorphism. So this darker shaded area means homeomorphisms from N to N prime. Then this blue path is a flow which starts at the identity and ends in this space of homeomorphisms, which then end to N, so it becomes a motion from N to N. So for example, we might take M to be the disk, and then these series of images shows a series of homeomorphisms from D to itself, from the disk to itself, progressing along a flow. And I've just added these grid lines so you can see the motion, and you can observe that this fixes the boundary. So this is a boundary fixing flow of the disk, which does this gradual rotation of the interior. And then we could consider what this flow does if we drop in 2 points as our subset of the disk. And so if we put 2 marked points, then we have this gradual rotation of the interior, and we see we get this braiding of these 2 points. And we can make this, we'll make this more precise in a second, the relation between braids and motions. And so then we showed, me together with João Faria Martins and Paul Martin, that we obtain a groupoid, which we call the motion groupoid of the pair MA, where our objects here are just all subsets of M. So this P of M means the power set of M. Representative morphisms. So representative morphisms are motions, and then our morphisms in the groupoid are equivalence classes of motions. Representative motions are composed very similarly to how paths in the fundamental group are composed. So if we want to compose the flow G with the flow F, we do F twice as fast. Then we do G twice as fast, but we have to compose with this F1 because all of our motions start at the identity. And so we have to make sure that these paths agree at their endpoints. So we have this slight adjustment here. So these compose just like paths. If we have a morphism, then the inverse of a representative motion is given by taking this F bar, which is just like the inverse in the fundamental group. Again, we trace the path backwards, but we just compose again with this F1 to the -1 such that we get something that starts at the identity. So what does it mean to be a motion equivalence class? Well, we have that motions F from N to M prime and G from N to M prime are equivalent if G bar star F is path equivalent to what we call a stationary motion H. So a stationary motion is one that fixes the set N that we're interested in for T. And the identity is just given by this path, which is the identity at all points. And so to make the relationship precise between the motion groupoid and braids, we proved that if we look at the motion subgroupoid associated to a configuration of n points in the disk, then this really is isomorphic to the n strand Artin braid group. So I know I'm going very, very quickly through the construction of the motion groupoids. The point here is not to take away a full understanding of the construction of this category, only that we have some category that generalizes things like braid groups that we already know play an important role in understanding topological phases of matter. And this construction that I'm detailing today is a way to obtain representations of these things. We also get that if we consider unknotted, unlinked loops in the 3-ball, so this is something known as the loop braid group, some of you may have come across. So the loop braid group corresponds to these loop particles living in 3 dimensions. So it's a generalization of the braid groups, this 3-dimensional setting, and we get these 2 types of braiding. One type is where we take 2 loops and we just move them around each other without either of the loops going through the other. And the other braiding is where we take one of the loops and we really pass it through the interior of the other. And these give 2 different braidings. And so we get, we have a presentation of this group where one of these braidings is symmetric and one of these braidings behaves like a braiding in the braid group. And then we have these mixed relations. And again, we can see this as a motion groupoid. Okay, but the key result I want to mention here is that we can explicitly construct a functor from the motion groupoid into the category of homotopy cobordisms that we just constructed. So how do we do that? We need to introduce something called the world line of a motion. So if we take a motion F, which goes from n to n prime, then the world line of this motion is given just by looking at the image of this subset n at each point t, and then considering that as a subset of M cross I, moving up I as the path progresses. So just precisely this braiding that I put on the slide before. And then we're going to define this W prime, which is just the complement of the world line in M cross I. And then to construct a functor into our category of homotopy cobordisms, we're going to need to put some finiteness condition on our motion groupoid. So we just denote by HF mod M the full subgroupoid of mod M, such that the complement of each object is a homotopy finite space. And so the kind of thing to have in mind that we're ruling out here is in the motion groupoid a priori, we could consider like a disk with an infinite number of points. And then the fundamental groupoid of the complement would be the free group with an infinite number of generators corresponding to these points. And that we don't allow in our category of homotopy cobordisms. So then we can construct a functor from these homotopy finite motion groupoids into HOMCOB. And what this functor does is it just takes an object in the motion groupoid. So remember, objects in the motion groupoid are just subsets of M. So it just takes a subset of M to the complement in M of that subset. And it sends a morphism to the homotopy equivalence class of the morphism, which goes from the complement of n to the complement of n prime. The space in the middle is just the complement of the world line, and then the mappings are just the inclusions. And there's some work to do, so the proof of this theorem, there's some work to do to check that the equivalence relations on either side really match up. But it turns out they do, and this really does become a well-defined functor. Okay, so that's the end of the section on motion groupoids. Is there any questions at this point?
I think the audience here missed the last 15 seconds. There was a glitch.
Ah, okay. What did I say in the last 15 seconds? Something about how to prove this theorem, I think. So the point is that the work to be done here is check that the equivalence relations match up, and that relies on some results that we proved in my paper with Paul Martin and Joao Ferreira Martins, that you really do get a functor here.
Thank you.
You don't say anything about this functor, like good properties, is it faithful, I suppose? For instance?
Right, that's a good question. So no, it certainly will not be faithful. You're definitely losing information because this homotopy equivalence relation we've put on this HOMCOB is really quite a sort of drastic equivalence relation. We're losing a lot of information by saying things are equivalent up to homotopy equivalence.
On the other hand, you're also quotienting out quite a bit on the motion groupoid, right? You have this equivalence of motions. Shouldn't that? Okay, but you're saying it's not. It doesn't make it injective.
Yes. Yeah, maybe I need to think about this a bit more. I can't think of an example off the top of my head. But my expectation would be that something is lost in this functor. But yeah, I need to think a little bit more about that.
Sure. All right, thanks.
Okay, so now for the last part of the talk, I'm going to talk about how to explicitly construct these functors, which these take as input a finite group G, and for each finite group G, give a representation from HOMCOB into the category vect C. Okay, so I wanted these constructions to be explicitly calculable. So I worked with base points. So I guess how you want to think about this depends on how categorical you are. If you're someone very categorical, you might say, why didn't you just start from the fundamental groupoid? To which I would say, the fundamental groupoid is infinite, and then I don't know how to calculate things very easily. So I want to introduce these base points to restrict to these subgroupoids of the fundamental groupoid. If you're less categorical, you might say, why not work with the fundamental group? And then what we're going to find is that things like composition become very difficult trying to define one canonical base point. So we're going to kind of go somewhere in the middle, and we're going to have a set of base points in each of our cospans. So the first thing we're going to do is we're going to take one of these cospan cofibrations, and we're going to define what we call based cospan cofibrations, where we add some base points to these cospans. So I'm going to use this boldface chi to denote pairs of a topological space X and a finite representative subset X0. So what I mean is just that there is one base point, one point in X0 in every path connected component of X. So then if we take 3 of these pairs, then we can define what we call a based homotopy cobordism, where this is a map of pairs, a cospan of pairs, such that if we forget about the base points, we get our old homotopy cobordism. I and J are maps of pairs. So what I mean by that is X0 has image in M0 and Y0 has image in M0. And then I also have this condition that M0 intersect the image of X must be exactly the image of X0, and similarly for Y. So I'm going to give an example on the next slide. So if we look again at this first example we had of a cospan where we had the disk and these 2 copies of S1. So if I look at my copy of S1 on the left, I could add these 3 base points as marked. This is a finite representative subset. In my other copy of S1, I could add these 2 base points as marked. Then when we look at the image in D2, what our conditions say is that the image of these base points S1, 0 must be in D2, 0. So we must get these 3 base points on the boundary. The image of this S1, 0 prime must be in D2, 0. So we must get these these 2 points on the image of this red circle. Then we're allowed, if we want, to add extra base points in other components of the disk, which are these green base points. But we're not allowed to add extra base points which intersect the image of I or J. So we're not allowed to add extra base points on this blue boundary or on this red circle, which didn't come from our original pairs. Okay, so now we can already assign a vector space to such a pair. So this is what will essentially eventually become our map on objects in our functor ZG. So I'm going to define this ZG exclamation mark of this pair XX0, and I'm going to define this to be the C vector space with basis the groupoid maps, so functors from this pi XX0, which is the full subgroupoid of pi x with objects x0, into this group G, where I'm just considering this as a one-object groupoid. Now, of course, this vector space depends a lot on the set of base points x0. So later on, we'll adjust this construction such that we remove the dependence on the base points x0. And let's just look at an example. So if we take our x to be the complement of these embedded copies of S1 in the unit square, and we take our x0 to consist of 3 points. So remember, it must be representative. And if we look at the unit square complement 2 copies of S1, that has 3 connected components. So the minimum number of points we could choose is 3, 1 in each path connected component. So we put 1 point here and then 1 point inside each of these disks. Then what is the fundamental groupoid? Well, it's generated by these loops, x1 and x2. So what we have is it's isomorphic to the free product of Z with Z. So that's just the fundamental group of disk with 2 punctures. And then disjoint union with these trivial groupoids, which correspond to these base points in the middle. And so then if we want to look at maps from this fundamental groupoid pi x x0 into G, well, G has 1 object. So all the base points, all these x0 points must be mapped to that unique object. So there's nothing to do there. We just need to look at where morphisms are mapped to. And we only have 2 non-trivial morphisms or 2 non-trivial generating morphisms in the pi x x0. That's these loops x1 and x2. So we define a map from pi x x0 to G just by saying what the image of these loops are. And so a map is given just by a pair in G cross G, just by choosing 2 elements of the group that we map these x1 and x2 to. And then we take the C vector space. Okay, so that's what our initial mapping on these pairs of objects look like. So then what we'd like to do is assign a matrix or a linear map to our based cospans. So let us consider one of these based cospans from xx0 to yy0. Now, the vector spaces we've assigned to x and x0, xx0, yy0, are inherently basis dependent. So we can really think of our linear map that we're going to assign to this based homotopy cobordism as just a matrix where the matrix is indexed by the bases corresponding to the vector spaces ZGXX0 and ZGYY0. So I'm going to use this physics-like notation where, so what this notation means is, so this ZG associated to this base cospan should be a matrix. And this notation says, look at the F column of this matrix and the G row. So what I'm defining here is the element of this matrix corresponding to basis element F in this vector space ZGXX0 and basis element G in this ZGYY0. And what does it mean to be a basis element in ZGXX0? Well, that just means it's a map from pi XX0 into G. And so what I define this matrix element to be is the cardinality of the set of all maps from pi mm0 into G, such that it commutes with this diagram where we look at the cospan and we look at these maps F from pi xx0 and G from pi y0. So we're just counting maps which commute with these cospans. And so the reason why this mapping seems like a sensible choice is precisely because it behaves well with respect to composition. So if we think of our composition of cospans extended in the most obvious way to these based cospans, then when we look at the composition and apply the fundamental groupoid functor, we have a diagram like this. So this is the kind of diagram we need to check to confirm whether or not our mapping behaves well with respect to composition. And so it's a theorem due to Brown that precisely when we have cofibrations, when our maps J and K are assumed to be cofibrations, when we apply the fundamental groupoid functor to this push-out square, so we constructed this composition by taking a push-out in top, when we apply the fundamental groupoid, this remains a push-out. So it's a push-out in groupoid. And what that means, being a push-out in groupoid, is that if we want to look at maps H from this composition that commute with these maps F and G, then they're uniquely determined by a pair of maps from pi mm0 and pi nn0. And if you follow this through, if you sort of write this down and look at it, what you find is that the number of maps H coming from the composition can be written in terms of the number of maps M coming from pi M and pi N, where you sum over maps from pi Y, Y0 into G, which is precisely what matrix multiplication looks like, where we sum over the index, sum over the rows of the first matrix and the columns of the second matrix that we're multiplying. So we really do get that this preserves composition. I don't know how much time I have left.
About 6 minutes, 6 minutes.
Okay, I'm going a little bit slower than I anticipated, so maybe I should skip over some things. So the point here is that we now want to look at what happens if we change the sets of base points. So we want to remove our dependence on base points. So the first thing we can do is just make a straightforward observation that if we consider these groupoid maps for any space X, and then we add an extra base point Y, defining maps from this new set of base points just corresponds to choosing where we send one path, and that's a completely arbitrary choice, so it just corresponds to adding a copy of G. So adding base points to our subset M0 just corresponds to multiplying by the cardinality of G. So what we can do is we can make this straightforward argument that if we change the base points so I'm going to skip over most of the details of this, but if we change the base points in our space M, then we can just multiply by this normalization factor and still get the same value out. So the first thing we're going to do is we're going to adjust this ZG exclamation mark map to be this new ZG exclamation mark with this normalization factor. And now it no longer depends on the set M0. And we have this X0 as well, such that it still preserves composition. Then we have to work a bit harder to remove the dependence on base points in the objects. So we do that by taking a co-limit construction. So the point here is that if we look at the fundamental groupoid of X with a set X beta, where X beta is a subset of X alpha, then there's an inclusion of fundamental groupoids. And this means that if we look at the set of maps from pi x x alpha into G, then by composition with this inclusion, we get a mapping into the set of maps X, X beta. And by taking a co-limit over all of these mappings, we can get something that no longer depends on our base points. So we can redefine our ZGX to be this co-limit over these maps varying the base points. And then to get a map on morphisms, we can just define we can just use the properties of the co-limit. So it turns out that this map on morphisms we define, the ZG exclamation mark, forms a cocone over these mappings which we took the co-limit over. So that means using the universal property of the co-limit that we get this mapping from our ZGX into our ZG exclamation mark y alpha prime for some choice of y alpha prime, and then you can use the map into the co-limit. And this, the thing to prove here is that this didn't depend on which y alpha I went through. And this amounts to proving that you have a map of cocones. This does work out, and this gives a functor. And we can write down by looking closely at what happens in this map. Using the universal property, we can get a very straightforward description of what this mapping looks like. So what we find is that the matrix element that we're assigning to a now equivalence class, F, an equivalence class G, is just given by counting these maps such that they're equal to some representative F, and such that they're summing over all G in the pre-image of the equivalence class, up to some normalization factor. But at this point, I said I wanted to introduce base points such that we had something finite and calculable, and then I took a co-limit over all these finite subsets, which is something very infinite. And so what I need is a result that says I really can get back to something finite and calculable. So what this result says is that this ZGX, this co-limit, really is equal as a vector space, or isomorphic, this should be as a vector space, to just choosing some finite representative subset and considering maps up to natural transformation. So we have some very explicit method of calculation. And then the rest of my slides are just examples of this calculation and what we get in specific situations. But I think I've run out of time, so I'll stop there.
Any further questions for Fiona? Yeah, go ahead.
Can I ask a question? So if I understand well, this functor you were describing is at least very closely related to Dijkgraaf-Witten theory, right? It describes flat G-value connections and surfaces. Now, it's been a while since I thought about this, but I think these kinds of functors have been discussed before, right? Could you say how your construction relates to what has been done before?
Yes. Yeah. So sorry, I was rushing a bit at the end. In some sense, this is kind of encapsulated in this final result here. So there's things like the Quinn finite total homotopy to QFT, if you've ever come across this, where similar maps are considered, but without adding in these base points. So what you get is something which you can prove as a functor, but can't really calculate in practice. And so what we do by this construction is show, this last result on this slide says that actually this co-limit gives the same thing as considering groupoid maps from the full fundamental groupoid and taking those maps up to natural transformation. So this really says that what we get by doing this different construction actually is the same as a specialization of the Quinn finite total homotopy.
Oh, I see. And do you need to or want to really divide out natural transformations? Don't you rather want to consider the actual groupoid, the functor groupoid, and do pull-push? You see what I'm saying? If I understood well, you're showing on the slide here, your quotient, you're taking the set of groupoid functors, right? Modulo natural transformations, right? I think there's constructions on there where people consider actually the full groupoid of functors and then produce a matrix from spans of those, if I remember well, by pushing.
That may be true. I would have to look at it. So I mean, I guess the way I see this construction is it essentially seemed like it was forced out of trying to get something that didn't depend on the choice of base points. It certainly isn't clear to me how you could construct something that really gives a functor without quotienting out by something. But maybe there are constructions and I'm missing something here. I'd be interested to see more about that.
Okay, any other questions? Gene?
Yeah, I'm sorry, maybe I missed it, but did you tell us why using Quinn-image cofibrations and not self cofibrations?
Yeah, so I think that was the same as Er's question earlier. You mean that I said I'd come back to it and then I skipped over it very quickly. I think really that's encapsulated back in the construction of the category where we need this theorem that says that our cofibrations play nicely with our equivalence relation.
I see. That makes sense. So I guess, are you saying the problem boils down to that you're really using like strong homotopy equivalencies and not weak homotopy equivalencies in your equivalence relation?
In what, sorry? In the equivalence relation.
Right, so using homotopy equivalencies instead of weak homotopy equivalencies, and I imagine
yes.
If you wanted weak homotopy equivalencies, then you would use cofibrations. Is this?
Yes, I expect that to be the case.
Okay. Thanks.
Oh yeah, so you started with like a physicsy motivation. So after going through this construction, could you say something about how, so for example, these submanifolds, which you're looking at the motions of, they're meant to be some sort of particle at the end of the day, right? So could you say something about how we could benefit from understanding particles in terms of co-spans, for example? Does that give us something? Or is there like an example you've worked through where you get different types of particles? Does that arise naturally?
Well, I think the point is, I mean, in the motion groupoid, you could choose any particles you want. So I think from that point of view, the kind of point here is that this is very explicitly calculable. So like I could explain to you how to calculate, for example, if you want to take the over and under crossing of braids and what precisely you would get. And you might say, well, we already know quite a lot about representations of braids. You're probably not going to give us a new representation of braids. Sure. But we might then think about instead motion groups of like knots and links in 3 dimensions, where we really don't know very much about what these, we don't even know presentations of these groups potentially. But we might still be able to construct a representation using this homotopical construction and obtain some particle statistics without having a complete understanding of what the group of particle motions looks like. Does that answer your question?
Yeah, kind of. I might ask you more stuff by email.
Yeah.
Very good. Any other questions? Okay, if not, let's thank Fiona again for the very nice talk. So we can